Okay, so good evening, all of you. And today is our last class. And as we discussed that I will be discussing one part which is still left, and that is called quantum error correction. Not a big topic, but very useful to understand as a part of the quantum computing topic. And the second, I will also like to discuss a little bit more about these transitions between the ion trap. Now, so I will talk about that only for 5-10 minutes. This class will go only for 1 hour, and from 7 to 8 p.m. Then I have already shared the final quiz to you, and you had to participate in that. And that is all from our side. So let me switch off my video so that we can avoid any kind of bandwidth issue, and then we can keep discussing. Yeah. Okay, so coming to our last topic of our this course, and that is called quantum error correction. So what I can say, it is a we will use the word QEC all the time. So it is a protocol. Okay, so quantum error correction is a protocol. Protocol means a set of rules, or you can say it is a framework. Is a framework protocol designed to protect information from error, and that error may arise due to maybe a decoherence, maybe arise because of the, let us say, gate imperfection, and maybe also environmental noise. So generally, in the classical computer, when there is a problems comes, this kind of correction required, then in the classical system, what you do a copy, you duplicate the information. And whenever you feel that the information seems to be lost, then you can just replace with the duplicate one. So in classical computers, This is done by duplication of information. And whenever you feel that the original information is lost because of some reason, then you can replace that information with the duplicate one. But in the quantum system, there's a problem, okay? In quantum computer or quantum system, we cannot duplicate. Because once you try to duplicate a state, and this can be done only by measuring it, and that duplication going to destroy or collapse the wave function, because the uh, duplication leads to wave function collapse. And that's why in the quantum system, you cannot make a carbon copy. Okay. So there's information, it is stored, that's all. You cannot duplicate the information. And in the quantum mechanics, this you can prove, okay, something called no cloning theorem. So in the classical system, you have the option. If you have a now fear that the actual information may get lost, then you can create multiple copy of that information. And if that information get lost, you can replace that with the duplicate one. But in the quantum system, you can't do this, because once you try to copy, the wave function going to collapse. You may copy it, but the original will going to lost. So only you have only one. This information will be stored only once. Okay, you cannot copy it. So you cannot copy any arbitrary quantum state according to the no cloning theorem. So the question arises, what to do then? So in the quantum system, when the question arises, what to do? Then there is a method in the quantum system that is called the syndrome. That is called the syndrome measurement. We'll try to understand. For example, you think about the cases no, of some therapies. No, think about the case of homeopathy, maybe Ayurvedic. So in the homeopathy treatment, they are traditional medicines. Doctor never going to do a test for the problem what you have. They only go for the symptoms or syndromes. So if you visit your homeopathy doctor or Ayurvedic doctors, what they will say, okay, tell us more about what kind of problems you are facing. So they will focus more on the symptoms or syndromes. For example, you say, okay, I'm coughing, okay, but coughing can be because of many reasons. But by asking more and more questions, if doctor is very experienced, he may guess or he may come to conclusion that this coughing is because of regular flu or some other disease or many other reasons it can be, and accordingly he can provide you a medicine. And this is exactly what we also do in the quantum computer for the error correction. A similar kind of pattern we generally follow in the quantum computer for the error correction, which I will explain you. So two things you must keep in mind. The first is no cloning theorem. So it is not allowed to copy state. And second is the syndrome measurement used for error correction. So this one we use for the error correction. And how we do it, let us try to understand. So in the next maybe 10-15 minutes, we will understand how this error correction is done. So for the error correction, the quantum circuit is the following. For error correction, circuit is that uh, we have our state that is called psi. Okay, psi is the state which you care. So if you want to, or maybe this is the qubit in the superposition, let us say this is the qubit in superposition which you are interested. So to preserve, see, you cannot make copy of this psi. Generally what you do, you create two more qubits and you initialize them in the 0 state. And these two states or these two qubits are called auxiliary qubits. Correct? And then you apply one CNOT gate between psi and the first auxiliary qubit. And then you apply one more CNOT between the psi and the second auxiliary qubit. So you can see this is a CNOT gate. So CNOT, you can say 1, and then CNOT 2. And then let us say that this is a system, and because of some reason, there is error comes in the your qubit. And because of this error, then the output will be changed. So you have this your initial qubit, which you are interested. Along with that, you create two more qubits and you reserve them as the auxiliary qubits. And then you apply C0 two gates on the first and second, and let this qubit remain as such. And because of some reason, let us say this E bit means error in the bit occurs. So when the error in the bit occurs, okay, so this error in the bit is like a gate. It's going to cause some changes, okay? And this change is going to change the bits, qubits. And after that, you will have something here. So whatever changes happens here after the, so this is after error occurred. So once the error occurred, then you have this one. So what you do after this, you apply one more C0 between first and two, another C0 between the first and the third. After that, you apply CC0 gate. Now we discussed this CC0 gate, and you will see you will get the original state back. This whole process, I mean, even if this error occurs between for the psi, with this process, you're going to uh, recreate that state again. And of course, these states will change. I'm not writing, but these states may change, but we are not bothered about this. These are not important for us. So this is the overall, I can say, quantum circuit to restore the original qubit. So maybe I think better that I will not discuss too much, but I think try to explain you through some example. Then I think you will be able to understand the how these error correction protocols works here. So let's take some example. So example, let us say we can talk about bit flip code, let us say. So in the example, what I'm going to take, let's say my qubit is in superposition, let us say alpha 0 and beta 1. So this is my initial qubit, which I have. So what I will do, let's see here. So this is the initial qubit here. And along with that, what I'm going to do, I'm going to create two more auxiliary qubits, 0, 0. And then I will apply C naught gate here and another C naught gate here. And let us say here in this region, some error occurs. Okay. And here, let us say I'm talking about the flip 1 bit, maybe due to noise. So let us say because of noise, the one qubit flipped. After that, it will change here. Then what do we do? Apply one more C naught gate here. Apply one more C naught gate here. And then apply here CC naught gate. Understand that this is the C naught. This is C naught, but this is the CC naught. Can you recall this this gate CC naught?
Toffoli gate. Toffoli gate.
So I hope you can write down the truth table for the CC naught gate. I mean, you're right, Toffoli gate. Okay, we discussed that. So this is 3 qubit gate. What it does, anybody will let me know what it does, CC naught gate.
If both controlled gates are in one state one, then only that target bit will be flipped.
Exactly. Okay, it's act like an AND gate, correct?
Yes.
Good. So this is so let's now we are discussing this example now and you will understand how it works. So here again you see psi is what I am care about. Okay, I want to preserve this qubit, and this is in the superposition state of alpha 0 and beta 1. And I don't know exactly what alpha is, what beta is. I'm not aware about this. I don't even want to know this also. So this is one qubit, and this is written in the basis states 0 and 1. So what I will do, I will create two these auxiliary qubits. So here at this location, then the wave function, okay, the system will be what? If you combine these two, so this is going to be a psi tensor product 0, tensor product 0. I hope it is clear to everybody. this becomes psi, tensor product, this become 0, 0, correct? And what is psi here? Look at that. If you put the value of psi, so this is alpha time 0 plus beta time 1 and tensor product 0, 0. And this will give what? Alpha. So you can see that the wave function here, let me call now whatever I can call, let us say phi. I can denote my next wave function is a phi, nothing but a alpha time 0, 0, 0 plus beta time 1, 0, 0. I hope it's clear to everybody. The dimension will change now. Earlier, the dimension of 2 was what? It is your 2-dimension now. This psi lies in a 2-dimensional Hilbert space. 0 also lies in the 2-dimension, correct? But now you have a 3 qubits. 3 qubits mean dimension becomes 2 power 3, 8.
3, 8.
Exactly. Now you are in the 8 dimension now. Okay. So this is because of 1 qubit only. So this is still 2 power 1 means 2 qubit, 2 dimension. This is also 2 dimension. This is also 2 dimension. This, when you only have a tensor product of this and this, then it will become a 4 dimension. Now this is going to become an 8 dimension. Okay. So this new wave function psi or phi, this will going to reside in a complex space or complex Hilbert space having a dimension of 8. Well done. Now let's come to the next part here. So you're going to apply this a qubit, okay, or this C0 gate on the first 2 qubit. So what will happen? Tell me, when you apply, so at this location, how this wave function going to look like? Anybody? You see here, you have a alpha 0, 0. Look at here. Now this is going to act like a control bit now. This is the control bit, and these two are for the first case. In the first case, this is target bit now. But when control bit is 0, nothing happened target bit. So this is going to become alpha 0, 0. And since nothing happened to 0 also, because I'm applying the C0 gate only in the first 2 plus beta. Now tell me what happens here. Anybody?
1, 1, 1.
No. You're applying the C0 gate only between the first 2 qubits, correct? It means that this one is going to act like a target bit. I'm not applying here, no, correct?
1, 1, 0.
It will be 1, 1, 0. Perfect.
Okay.
And now this is the wave function. And now you're applying second C0 gate between first and the third one. So here, what happens then? At this location, tell me what happens. It has become alpha. Now this become target now. This is the target. And this is target. So because control is 0, so this will become 0, 0, 0. Nothing happens. Plus
1,
beta. What happens?
1, 1, 1.
1, 1, 1. You can see that. So this is the final, now I can say the state which going to be appear after applying this 2 C0 gate. I hope you are comfortable with everything. So if not, then I can again write, see, when you apply on the first, let us say alpha 0, 0, 0 plus beta 1, 0, 0. When you apply the first C0 gate, then this bit and this bit is going to act like a target bit. And this is going to change alpha 0, 0, 0 and beta 1, 1, 0. Again, you apply the C NOT gate. What you will get now, again, this is going to act like a target. This is going to act like a target. So you're going to have alpha 0, 0, 0 plus beta 111. Now, can you see what kind of state this is?
Bell state.
This is the Bell state, entangled state. So you have created an entangled state. And now that's why you can see here that this process, the process of entanglement, why this is so important. Everywhere you need it. You have to create entanglement between these qubits. And physically, how we entangle two states. Do you remember in the last class, I explained this concept in the ion trap, correct? In the ion trap, both in the calcium case and also in the panning trap, how to entangle the qubits by shining lasers in the blue sideband and the red sideband, correct? First with the pi/2 pulse and second with the pi pulse. Can you remember? So this is the mathematics, and you also know the physics behind that, how to do physically in the laboratory, how to entangle qubits together. Now, coming back here now. So let me remove this. Now see, we have the some noise in the system, some noise going to happen. So imagine that some noise is going to cause a flip in the spin. Just imagine you are very unlucky and the first qubit flipped. So because of noise, let us say due to noise, the first qubit flipped. If the first qubit flipped, then at this location, what you will get? Look at alpha, the first qubit, this one. So this 0 become 1, 0, 0 plus, then this is going to become, because they're entangled now. So if this is going to flip, other also going to flip now. This becomes 0, 1, 1. Agree, everybody? So this is because of the noise. The first bit flipped. Now see what is happening here. You're going to apply the first C NOT gate here. So tell me, can somebody tell me what will going to happen now in the first state? Yes.
Becomes 110.
110.
It becomes, yes, exactly. It becomes 1, 1, 0. What happened to second one?
Yeah.
Sir,
It is
same
also
रहेगी.
It remains the
0,
same
1.
because control is 0.
Yeah.
Perfect. Then apply the second C NOT gate on this one. Okay. Tell me what happened to first one. Come on, please.
111.
It become 1, 1, 1. Perfect. What happened to second one?
010.
No, it is 0, 1, 1. Correct?
01.
Because
Yes,
still the control bit is the 0, no? Correct?
0. Yes.
The second one will remain 011.
Yeah, exactly. And now see here. This is CC NOT gate. So what we will do, if here you can look at now in CC NOT gate, the first is become a target and the last two are the control, correct? Agree? You see now the nodes act like a control. And where you have this plus sign, that become the target. Agree? So in the control CC naught, what happened when you have a, let us say, this is 0, 1, 1. What will happen? It become 1, 1, 1. But if you have, let us say, 0, 1, 0, then what you will get? 0, 1, 0. Nothing will happen. If you have 1, 0, 1, it still remains 1, 0, 1. Nothing will happen. Okay. Only when the both controls are 1, 1, then this will change. So tell me, what happened to first one?
0, 1, 1.
0, 1, 1. Perfect. What happened to second one?
Because 1, 1, 1, right?
1, 1, 1. And now you see, look at the first qubit. Look at the second of the first qubit. They are 0 and 1. Look at my original wave function. In the original function, first is the 0 and second is a 1. I'm not bothered about these two. They are the auxiliary qubits. Okay. I'm not bothered about this. For me, what is the most important is the first one. And I got them back. You can see that this is how one can do the quantum error correction. How to recreate the original bit which have been flipped because of some noise. And this is done by the entanglement. Entanglement here plays a very crucial role. So that's why I told you in the quantum computing system, the first thing is the qubit you need. The second thing, you have to put them in the superposition. Then third is the entanglement. And fourth is the interference. So they are the processes. This is not a process. This is a physical quantity, but superposition, entanglement, interference, they are the processes. So these three processes are very crucial in the quantum computing. I hope everybody understood what I was trying to convey here. And just imagine, think about what if no spin flips. Let us say, now this is the acting, now is working when the spin is flipping or bit has been flipped. Imagine if there is a no flip. If there is no flip, then look at what will happen. This is of course remain the same here, up till here the same, I'm right?
Yes, sir.
And here what you will get? Nothing happens. You will get a 0, 0, 0.
0.
Plus beta 1, 1, 1. Red one is the new one I'm getting. Now look at, you apply the first C0 gate. Tell me what will happen? 0, 0, 0. Nothing happened. What happened to second one?
1 0 0.
1, 0, 1.
Oh, sorry, 1 1. Sorry.
And then apply the second C0 gate. What happened to first one? 0,
First
0.
one, nothing changes.
And what happened to second one?
Second one, 1
0, 0.
0.
Yes.
And let us come here now. Now look at the two control bits. They are the same. Nothing happened to the target bit. Again, two control bits are 0. Nothing happened to the target bit. You see, you got the original one again. So even if the bit flipped or not flipped, in both the cases, this circuit works. It is going to give you the original qubit.
Sir, how do you know at which point of this circuit this flip is going to change? Because you have put that flip won't be due to noise after 2 C0 gate.
Yeah, this this C0 gate is always applied at the initial stage. Okay, and they remain entangled. Whatever happened doesn't matter. Okay, let them happen. Okay. See, in the quantum mechanics, you have now the processes, and depending upon the, let us say it is just a summation, you are doing a sum. It is a one step process only. Okay. So once the you create a superposition, at the same time, please create the auxiliary qubits and then entangle them. Okay. Then you do your calculation, and then after that, no, entanglement is done already. And once you try to do the calculation, there you apply this no, error correction part.
Sir,
But
one
if it
question
is
is,
let us say if it is a multiple step, then you have to apply multiple stages, not error correction. This is the reason that people are more suffering, because for every correction, then you need a auxiliary qubits. Okay, so just to safeguard one qubit, you need 2 qubits spare, and then you have to entangle them. So when we say now, like if you have a 300 qubits entangled qubit, then this is actually equal to 10 to the power 19. Okay, and you can map the whole universe. This is not a true. Okay, because just to support 300 qubits, you need twice higher than now. For each qubit, you need twice higher. And if you entangle more qubits together, then you need more and more number of auxiliary qubits. So maybe if steps are higher, then for one qubit, you may need 3. It may become 4. It may become 5. It may become 6. It depends number of steps you required in your calculations. Every step you have to safeguard your superposition state. Every step. Let me now give one more example. Or it's fine. I think it is
Okay.
done. If I think, then what you can try yourself. No, you can do yourself some other cases. Let us say, what if second bit or second qubit flipped? Then check yourself. What if third qubit flipped? So you will see that no, nothing happens. Okay, if second qubit flip, first qubit flip, doesn't matter. In all the cases, you're going to get the same answer. You will be able to restore your qubits again. So that is the beauty of this error correction. But this error correction then required huge number of auxiliary qubits, and they must be entangled together. And you know, the biggest problem in the superconducting qubit or superconducting quantum computing system is that you can entangle. Okay, you can apply gate on only adjacent qubits. So only the nearest qubits which are adjacent to physically adjacent, right? When I say adjacent, means physically adjacent. So one qubit here, another qubit here. If there is a here and one here, okay. Let us say this is the your center one, okay, like this. Then you can only entangle, only apply the qubit only on these 4, okay. You can't now make qubit between these 2. And if you want to make apply gate on the first 2 and third, between 1 and third, what you need to do?
swap gate.
You have to apply a swap gate. Okay, so you do swapping between which qubits?
2
In
and
this
3.
case, 2 and
2
3. You
and
have to swap 2 and 3. I think you are very well now familiar now with the system. Okay, quickly, since I have only 20 more than 20 minutes less, let me now give you one more point now, because there was a wrong information conveyed to you. here. So let us correct that no, that part. So when we talk about this calcium, so when you have a calcium, let us say 1 plus, so this is actually 3p6 and 4s1. So in the ground state, the configuration is of course is a 4 2s half. But when the electron excite, so it is go from 4s0 to 3d1, and there you're going to have a 3d 5/2 and 3/2. There are two metastable states are produced. So when I say metastable states means um, no electric dipole transition, no even transition. Means between this state and between this state, there cannot be any electric dipole transition. Okay. So what the wrong information we actually now in hurry, what we now came to in the previous class that key, we thought that this can go from the p orbit, p state. No, the transitions of course takes place only here when you're going to shine laser of 729 nanometer. Okay. But question that key when they are because here electric dipole transitions are those transitions in which the delta L must be a 0 and plus minus 1. So of course here in the case of D, you can see the L is 2. In the case of S here, L is 0. So in this transition, the delta L is going by a plus minus 2. So because this is the violation of the conservation of the angular momentum, capital L, so this transition cannot go through the electric dipole transition. But this can go through a electric quadrupole transition. That is called the electric quadrupole transition. And in this transition, the delta L is actually a 0 also and plus minus 2 also. Okay. So that is the conservation law now in the case of a delta L. So delta L plus minus 2, if there, then this can occur through the electric dipole transition. Now see, those students who are not familiar with these multipole transitions. So let me just just a minute. I want to go back to my keep it here and yeah. So here we can explain about this a little bit. So I was telling you that if you are not familiar with, let us say, electric dipole or quadrupole transition, then I can say there are transitions called E1, that is called electric dipole. Then M1, that is called the magnetic dipole. Then E2, that is called electric quadrupole. Similarly, M2, then similarly E3, then M3, and so on. Higher orders, you can say. This is the most simplest transitions in which the delta L is actually a plus minus 1. And in this case, the delta L is a plus minus 2. Okay. This is the most simplest transition in the nature. And this occurs very fast in the time period of 10 to the power minus 9 seconds. But let us say if there is a electron here in the excited state, and this is want to come to the ground state. So this electron will first try to figure out whether while making a transition to the ground state, if there is a possibility of now changing delta L by plus minus 1. Remember the photons always carry delta L plus minus 1 because of the polarization.
Laporte's rule or something.
Exactly, because of polarization. In fact, it is not correct to say it is actually because of the spin polarization. But even now, they also carry angular momentum, even because of their now I can say what I can use the word. There is special word I forget about. Anyway, let me use the word orbital. Okay, I will explain maybe. So this is because of polarization, but this is because of the field gradient. So this electron, let us say, if is producing a photon, and since photon must carry an angular momentum of, let us say, plus minus 1 h cross, so this electron must lose angular momentum of a 1 h cross. Okay. So if it is the losing 1 h cross, that's fine. It will go through the E1 transition. But let us say if it is the changing angular momentum by 2, now for example, it is here, it is a D state and here is S state. So in this case, electron must lose 2 units of angular momentum. So this cannot go through the E1 transition. So it will try to the other modes also. So it may try to go through the M1, E2, M2, E3, but then the process become little bit delayed. Okay. So it will take more time to come down. So that's why higher multiple transitions are delayed transitions. Okay. They are always going to have a longer time. Clear? I hope this picture. Or any question you want to ask about these multiple transitions?
Sir, one thing to ask.
Mhm.
That is here in case of dipole transition, that is delta L is equal to plus minus 1. That is the angular momentum gap. But previously you show that you in the previous picture you showed that and yesterday also delta L is equal to 0 plus minus 1. That is
Oh, that is
ml.
that is a capital L, correct? You understand, no?
Okay, small l should that is capital L and that is it will be
Exactly,
ml, the
exactly. Yes.
z component.
This is
Actually,
not
this
angular momentum, okay? This is symbol, right?
okay,
Symbol of the vector addition of the angular momentum.
okay.
See, I can give you one more analogy to understand this now. Maybe very funny analogy, but I think you can understand like this way. So let us say if you are standing on a multi-story building somewhere here. Okay. Let us say 100-story building. And let us say you want to come down. Okay. So the fastest way to come down, okay, of course, don't jump from the building because then you will not be able to survive. Means you want to survive also, and then you want to come down. Okay. What is the fastest way? You come through a lift, correct? Agree? Or maybe let us say if you have some protection here, let us say you have some kind of net already there,
Yes.
then you
yes.
can even jump also, correct?
Okay.
That is the most fastest way to come. So I can say, let us say if you have protection there to come down, then the first way is that you can jump. Okay. It is the most fastest time, fastest way to come down. This is equivalent to a E1. But let us say if there's no protection here, then you cannot allow to jump.
Oh.
Then what you can do? Then you can come through the lift, correct?
First,
So the lift is the second fastest mode, right, to come down. Let us say light is not working, lift is not working. Then what you can do? You can come through the stairs, correct?
Yes.
So finally, you have to come down. Okay, maybe by jumping. If not allowed, then you can go through the lift. If not allowed, you can come through the maybe through stairs. Okay, even stairs not work, then you can maybe you can take help of the pipes and then you can come down. Okay. So you will try to come down. So when electrons are in the higher state, they have to come down. They will try to, I mean, this transition can go through E1, M1, E2, M2, E3, M3. Even if all not possible, okay, which is called a radiative way to make a transition, okay. Even not possible, then this electron can come through a physical collision, correct? So through collision, it will going to give up its energy. And let me little bit now work on the we still have a 6 minutes. So I mentioned that you have a state called 2s half and 2d 5 by 2. So these transitions I'm trying to make here. So how you can make it? By pushing the incident laser. Now in this laser, what you can do? So because this is here, this delta L must change by a plus minus 2, correct? So this cannot go through the E1 transition, not possible. So it can only go through the E2 transition. But then you have to do a quadrupole transition. Okay. Now look at the shape of D. So this D orbit, how it look like? No, like this now. This is the electron cloud now. And how the S orbit look like? Spherical, correct? So you want to make a transition from here to here. It's not possible. So what you can do, you can actually put this atom now in electric field, which is going to have a let us say some kind of electric field gradient. So if you can create a laser which has a electric field gradient, okay, then this laser can actually deform the charged electron cloud of the s orbit in the s orbit. So what we can do, that you can do by a tight focused laser. So if I if I try to create a laser tight focus, so what will happen that, let us say like this way, and here the intensity is very high, and as you go now up, the intensity reduces, let us say. So if you look at the profile of the intensity, it is going to have this shape. So intensity at the center is very high, and intensity is going to decrease when you go away from that. Okay. So if you put this atom in this kind of laser, then this electron, which is spherical in nature, so when it is going to, let us say electron is somewhere here, okay, is s orbit electron cloud, then you can see this portion is going to see a higher field, this portion is going to see a less field, correct? Are you getting this part?
Yes, sir.
So electron cloud, then it is going to get deformed, right? Fine, comfortable.
It's fine, sir.
So this is going to create a deformation in the electron cloud, and then this deformation actually, once it is now getting matched with the D cloud, then this transition will take place. So this cannot be done. This transition cannot be done if electric field is uniform. Okay, for example, a plane wave. So in the case of plane wave, when light is traveling here, for example, so everywhere the intensity is constant, correct? So when you plot the intensity here, so intensity is going to be constant like this everywhere. But when in the case of the, let us say, this kind of laser, when the light is passing through, so the intensity when you're going to plot, it is going to have this shape. So if you want to create, let us say, quadrupole transition, then you have to create this kind of electric field. Okay, you have to create a gradient of electric field, okay, along the x-axis, along one direction. In the case of even transition, you only need a uniform electric field, okay, because you have to just push it, okay, on one side. You can just think like this way. Let us say this is the some kind of membrane, and in the case of even transition, you're going to push uniformly, okay, so everything will going to push. But in the case of let us say in the case of this situation, so electric field maybe here is very high, electric field here is less, less and less, and you can see that in this case this cloud is going to get torque, correct? So torque is going to introduce in this case. And you can see this delta L plus minus 2, from where the electron getting 2 unit of angular momentum. So it will get 1 unit from photon, which is coming. So the photon is carrying a delta L plus minus 1, and extra 1 unit it will get from the field gradient, because the field gradient also having a torque, and that when you have a torque means you have a angular momentum. So this electron in the ground state, it has a L equal to 0. To go to the D, it must get 2 unit of angular momentum. So this get 1 unit from the photon and 1 unit from the this specially designed electric field. I hope this is clear now. Okay. So in that situation, yes.
Yeah, this technique is interesting, but only my worry is if this electron has to feel the gradient, then the focus should be of 1 nanometer, right? Or maybe even
Exactly.
less than.
Yes, this is true. Not one. It should be. I can tell you, it should be a 0.1 nanometer.
Yeah, but I mean, so it's like you are already using about 800 nanometer laser, because the laser that you are applying is about 800. That's what I remember.
See,
But
what
then,
no, I understand your point. What I'm trying to say.
yeah,
See,
yeah.
even if you have a large focus, okay, even if you have a large focus, so still, I mean, so if you look at the gradient, okay, so it will have a gradient, correct?
Right, right. Yeah, I
So
understand.
even if you are, let us say, this whole is this whole system is, let us say, in the micrometer, correct? So even if the atom is somewhere here, okay,
Yeah.
it will going to see the gradient. Okay.
Yeah, but in one of our calculations, only if you focus it down to 1 nanometer, then only electron will feel any gradient. Otherwise, on its length scale, it's practically flat. I mean, I'm not questioning it. Maybe
Yeah.
I'm just raising a concern. And then for one of our paper, the referees comment was how you are beating the diffraction limit. For example, practically 800 nanometer laser focusing down to 0.1 nanometer. We need some special techniques, like maybe, I don't know, and so some different photonic techniques might be needed, probably. I'm not sure. Yeah, I'm just raising my concern. I'm not questioning here.
Yeah.
Yeah.
No, that is a really valid question, because you cannot bypass the diffraction limit.
Right. Yeah.
Definitely. I mean, in the E2 transitions, we need this electric field gradient. And let us say if I'm using, let us say 700 nanometer, okay.
Yeah.
So that is definitely going to be much bigger than the atomic size.
Yeah, we had simulated this kind of a Gaussian profile for intensity, but we had to taper it down to 1 nanometer to get at least some change in the energy for the electron. Which, as you said, it's right, but then the practicality, that's the only thing I was concerned about.
See, I have never worked in this in this case like you are working, but I'm still very much convinced with the logic that
No,
even
logic is perfect. I mean, I like
even
it.
if you are having this hill is very long, okay, so even if the atom is sitting here, it's going to see that gradient, okay. So maybe you can discuss with some optics people who are working, and maybe because this is something, this is how this ion trap people do. They are using normal laser light, okay, 700, and they are exciting this quadrupole transitions. So this is done simply. I mean, you cannot focus. I mean, this is going to be a 700 nanometer. And this atomic size is going to be only a 0.1 nanometer. So I'm very much sure this is only logic working here. I mean, that is the gradient giving the slope.
Yeah, right. No, the technique is quite convincing, not a problem at all. But only the dimension, that was only worry. Yeah, but we will check it. Yeah. And what about the transition probability? Because
it will be less, definitely. It is going to be less than the E1.
Less than the E1, right?
Yes,
yeah.
definitely it is going to.
But this is assisted through dipole. That's also one thing, no? Photon is giving a dipole.
It is
it's mediated in some way.
Yeah, I mean, so if you try to think classically, then quadrupole nothing but two dipoles actually, okay, in the opposite directions.
Right.
So to all of you, I have just extended the time of my test for it will now start from 7:10, okay, because we are still here. So I have just changed the timing. I hope you still cannot open now. You should not start. Can somebody check the link I shared?
Yes, it doesn't start.
Okay, good. Okay, so that's all from my side now. So
Sugam, can I just ask one question?
Yes, please.
Yeah, sorry. Yeah, so in the first part, you had this auxiliary qubit. So is that the ancilla qubit that you mentioned?
Exactly, that is ancilla qubit. Yes, that's correct.
That is ancilla qubit,
Yeah,
because I remember the name you mentioned, ancilla qubit.
Yes, sir, that is ancilla qubit. Yes,
that is the one, no? Right.
You call auxiliary qubits or ancilla qubits.
Okay, yeah.
So we had a limited time. I mean, you can see that if really we want to understand this quantum computing course, then definitely we need much more time, 3 to 4 times higher than what we have devoted here, right? We tried our best to understand at least how the system is working, and maybe we have a plan to now do this kind of courses regularly because this is the emerging field, and this is the way I think we can encourage many students, okay, to jump in this new regime. Okay, so maybe if you want to share any feedback so that we can improve it further, then it will be very useful for us. Or else I think that is the final word from my side. Yeah.
Sir, good evening.
Good evening.
Yeah, I'm Aarti Ganeshan from JBAS College from Chennai. So actually, this is the first time I'm attending a course on quantum computing. Actually, the way you took the class right from the basics of quantum mechanics, I think it was really very nice. And the supporting documents which you are giving and the recorded lectures, I think is really helpful. Actually, I really thank you for this course. And I think I'm sure like I need to again go through all the notes again, and to get the complete hold of the thing. I think it's a very vast area. So otherwise, you have given us the path, like what comes next. So since this is first time I'm hearing about it, I think I will take it this way, and it is really useful. Thank you very much, sir.
Thank you. And in fact, I can share one thing that I will I will share you the complete file, okay? Because I am making this file parallelly, okay? So still this hardware part is not yet given to you. So and also the Deutsch algorithm. So I will give you all the file completely so that you can refer it later on for the further information.
Thank you very much, sir. Thank you. Yeah.
Yeah, thank you, Sugam. It was absolutely Great experience. Thank you.
Thank you, Jovin.
Yeah.
And
Yeah, we will interact later.
yes, definitely.
Yeah.
So I think then we can close the session here. And now I think you can start now attempting your test. And this WhatsApp group will still remain alive for a few more days until we now distribute your marks. And mean that time, if you have any questions or doubts, please definitely you can share. Okay, that's all from my side. Sunil?
Yeah, thank you, Sugam, for this amazing lecture series. I'm pretty sure all the participants have benefited a lot. I think it is just a beginning of something which is supposed to be achieved over a longer period of time. Yeah, so I think this we should also continue with a more lecture series in the future. There is a lot of scope for this. So I think now it's the time for the test. We should stop here,
Yep.
right? Yeah.
Definitely.
Okay. Thank you. Thank
Okay.
you for everyone for
Okay.
attending. And let's stop here. Conclude it here.
Yep.
All right.
Okay. Thank you, everybody.
Thank you, sir.
Bye.
Thank you, sir.